Okay.
Okay, start.
Okay, very good morning. So in continuation with the earlier lecture, in today's session, we will look how to come up with a stick diagram for any Boolean function. So the earlier class, I think we have stopped somewhere here. How to make a stick diagram and a layout for NMOS and a PMOS. Taking this, let's see, like I would like to come up with a stick diagram for an inverter Y equal to A bar. So A is my input and Y is my output. Output is a complement of my input. To do this, again, I can make a schematic diagram or a CMOS diagram for the same. Already we have seen this, how to make a CMOS circuit for this function, a Boolean function. Here the function is very simple, where you have only one variable. The CMOS implementation for this is, you have a PMOS at the top and an NMOS at the bottom, and at the top it has been connected with VDD, and the bottom it has been connected with the ground, and both the gate has been connected, and that has been taken as my input A. The drain has been connected, and it has been taken as my output Y. This is a simple schematic CMOS structure for the function Y equal to A bar. Remember, this is my source, this is my source, these are my drain, and these are my gate. As I said earlier, this schematic is being drawn for this CMOS structure. Now, if at all, if we want to go with a stick diagram for the same, as I said earlier, you simply translate this PMOS and NMOS to the corresponding layer information. So let's first take two things. You have VDD and the ground. So the stick diagram is for the same is, you have one layer at the top, this is the metal one layer, and another one metal layer at the bottom. Remember, the color denotation for these two are blue color, as we discussed. So these are my metal one and again another one metal line. These two are parallel power rails. This power rail is used for VDD and this power rail is used for ground. So we have finished this VDD and the ground information. The next thing, I am supposed to get this PMOS and this NMOS. How do we get a PMOS? Yes. To get a PMOS, you draw a P diffusion. Over that, you need an polysilicon. So this is my poly. This is my P diffusion. Now again, similarly for my NMOS, you have one N diffusion, and on the top of that, you have a poly. So this is my poly. So this will culminate to a PMOS, and this will give me an NMOS. When once a poly crosses an N diffusion, this gives me an NMOS with source and drain to be one end. Similarly, source and drain to be the other. Now, source, drain, and this is my gate. The poly line is your gate. Now, only thing is, I am supposed to connect this source with the ground. To connect the source with the ground, I use again the metal layer. Now, this is my metal, this is my N diffusion. I am using the same metal layer. These two are the same metal layer, so this doesn't require a contact here. But at this point, you see here, this is my N diffusion, this is metal 1. So these two, to make a contact, I put a cross mark to indicate that these two are tied up, which refer to this source being connected to the ground. Similarly, this PMOS source need to be connected to the VDD. The same rule I am following here. Extend the metal line, connect that to the source. Again, remember these two are different metals, different layers. So I am putting a cross to indicate that these two are in touch with each other. Then I am supposed to connect the drain of both and take my output. Remember, these two are different materials or different layers. One is P diffusion, another one is N diffusion. Now I am using a common metal line. Metal and a N diffusion. In order to have a contact, I am using a contact there. Again, P diffusion and a metal, I am using a contact here. From this point, I am taking my output. The output is Y. So we have finished this output, source point connection, and only thing is I am supposed to connect both the gate and give my input as here. So this is my poly, this is my poly. Now you have a broken poly, you can simply connect these two poly and give that as your input. So this point is my E. Again, remember, the material which I have used is, this is metal and these two are poly. So these two are two different material. So I place a contact at this point. Because this is metal, this is also metal. Whereas this is poly, this is poly. This piece of line is poly. Very simple, that's all. So this will lead to the stick diagram for the same inverter. Or if I want to convert this as a layout information, simply extend this with appropriate layer with corresponding dimension of the width, corresponding dimension of the spacing, corresponding dimension of the overlap. That leads to the formation of layout. We will look at this layout, how to draw the layout or how to convert a stick diagram to layout shortly. Before that, we will still look with a couple of examples how to come up with an efficient stick diagram. So this is a very trivial example where we have taken a function of inverter, and for that we have drawn a stick diagram for the same. Similarly, the same thing could also be extended for, say, I am using a function y equal to a plus b the whole bar. This is a simple NOR gate. The implementation of this NOR gate goes something like this. I have AB. The schematic structure for this one is AB means two NMOS transistor in parallel. I am doing that, and the PMOS structure should be in series. So you have two PMOS, A, B, this is A and this is B. And the bottom one has been connected to ground, top one has been connected to VDD, and the drain has been connected, and here you get your output. This is the simple thing. Now, if at all, if I want to draw a stick diagram for this, I can draw the stick diagram for the same, something like this. A very rough, unoptimized way of drawing the stick diagram for this particular schematic is, you can very easily understand that these two are my NMOS. So, one N diffusion, another one N diffusion. Over that I put a polyline. So let this be A, let this be B. This is typically same as two NMOS transistors. Similarly, on the top you have two PMOS. So I put 2P diffusion and they are being crossed by a polyline. So this is my A, this is my B. These four structures represent four MOS transistors or stick diagram representation of the MOS transistors. Same idea. At the top I have my VDD, at the bottom I have my ground. Now simply you are supposed to add up this source and connect it to the ground. So if at all, if I consider this to be the source line, connect both the source line and that need to be connected to the VDD. So what I am trying to do is extend this metal line. Let I use a metal line and connect this to source with this ground. So typically I am connecting these two source and connecting that to the metal line ground. Similarly, A and B are my gate terminals. The same thing could also be seen here. For a MOS transistor A, I am supposed to connect that to metal line VDD. So extend this and connect here. Two different lines, so I am using a contact there. Similarly, look at this point. This is a PMOS. Both are PMOS. And this drain and this source has been connected. So I am supposed to connect these two by a metal line. I am using two different metal layers, so I am using a contacts here. One more thing, these two drains plus this drain need to be connected. Again use a metal line for this. Use a metal line to connect these two drains. Connect again with this, and here you can take your output. Yes. This is true or this is correct. There is no doubt about that. If you convert the stick diagram into exact layout information, this will act as a 2-input NOR gate. But the question is whether this is an optimized one. If we put the question whether this stick diagram, which eventually being converted to a layout, is going to be an optimized one, then definitely this particular stick diagram, whatever you have drawn, is not effective by all means. The main reason for this, remember, for converting this schematic information to a layout information, every layer is being associated with some other layer which lead to the formation of the capacitance. So having seen here, this particular stick diagram can come up with a layout and it can also give functionally the same result. But only problem is, if you look at the diffusion, here we have a broken diffusion here. Means I kept one diffusion here, another one diffusion here. One diffusion here, another one diffusion here. Or the P diffusion has been broken up at different points. Or the diffusion is broken. Since the diffusion is being broken, which naturally lead to more amount of interconnections. This lead to have more amount of interconnections, more amount of metal layers to be high, which subsequently lead to have more amount of parasitic capacitance, which again leads to more amount of delay, more amount of power. So in this stick diagram, though this is functionally working, the problem which we find is, since I have broken this N diffusion into 2 and P diffusion into 2, I simply went on for randomly converting this schematic to a stick diagram and subsequently to a layout, which led to having a broken diffusion at many points, and thereby you come across too many interconnections and too many capacitance. Thereby it leads to too much of power consumption at the delay. Now the next question is there any way to come up with an optimized layout or an optimized stick diagram? What is the best way to do that? Or what is the way available in order to come up with a layout which is optimized in terms of area and power? Now let's see what is an optimized stick diagram, or which stick diagram I call to be an optimized one in terms of area, power and speed. If I want to say it is optimized, it is supposed to have this condition. The diffusion should be a shared diffusion, not a standalone diffusion. Means I am supposed to have a shared diffusion in my layout. To have a shared diffusion, I am supposed to follow the order of polysilicon. The order makes a difference. In order to ensure a shared diffusion, thereby I will not have a standalone diffusion for each and every MOS transistors. So to come up with an optimized network case, the first and primary job is you need to have a shared diffusion. To have a shared diffusion, you are supposed to find out what should be the order of poly. By order of poly, what do I mean is, say suppose I have 4 variables. The poly lines represent the gate. We have already seen that. If there are 4 variables, I may have the order of poly to be A, B, C, D, or A, C, D, B, or it could be in any order. I can reshuffle this 4 variable in different orders. But the question is, which order of that poly will give me a shared diffusion, thereby it gives me a minimum amount of capacitance, minimum amount of delay and the power. To figure out that order or to find that order, you have the help of a graph theory which is being supported by Euler's theorem. Euler's theorem. Or again, the Euler's theorem is used for finding out the sequence of a poly line that need to be laid on my layout so as to have a shared diffusion, because a shared diffusion will give me a minimum amount of capacitance. Okay. Now what does this Euler theorem says? Very simple thing is, let's take a Boolean function and see that whether that Boolean function could be drawn with the stick diagram, an optimized stick diagram using this Euler's theorem. Now I am taking a simple example, Let me have a function a plus b c the whole power. This is my function. I would like to implement this function for a stick diagram for this, and I need to make sure that the stick diagram is an optimized one. So the simple job is first go for a CMOS implementation of the same. So very quickly I will go ahead because this has been discussed in the earlier session. So B and C are in series, so I will take this B and C. A is in parallel, so keep this A. That is my A function. So I am just connecting all this source, and this has been connected to ground. On the top of that B and C should be in parallel for a PMOS. So I am just putting those two in parallel, A to be in series. Yes, this is my A. On the top you connect by VDD and connect the drain of both, take the output as well. That's all, simple. Now this is my CMOS implementation of this function A plus BC. Now I am supposed to go with Euler theorem for this in order to come up with an efficient way to draw the stick diagram and thereby efficient way to draw the layout. Now let's see what is this Euler theorem says. The rule for this Euler theorem is something like this. Convert this schematic to nodes and edges. That is, all source drain of a transistor is being considered as nodes. Right? Or it is also called as vertex. And the gate is being converted as edges. Gate G is represented as edges. Okay? So it's something like this. So if I am having an NMOS, in order to represent the graph, I will represent something like this. This source and the drain are my nodes, and this gate is being represented by edge. The edge is simply a line connecting this. So this is my G. So this is a graphical representation of an NMOS. Typically that is applicable for a PMOS also. So the first and primary job is convert this schematic network to a corresponding graph theory network. Second, this is the first point. Second point is, make sure it's like a salesman problem. You are supposed to visit all the nodes, all the edges, but only thing is, the edges should be repeated only once, but the nodes can be repeated. So what does this Euler theorem says is, you are supposed to visit all nodes and edges. Edges should not be repeated, nodes can be repeated. Nodes can be repeated. Whereas edges should not be. Understood? That's all. So like this, you come up with a visiting pattern for all the nodes and all the edges. The third important point is, whatever pattern you apply for NMOS network, the same pattern should also satisfy for a PMOS pattern also. That is, the path pattern for P and NMOS should be the same. That's it. So if you make these three things to happen, then you can find out what should be the order of the poly, and thereby you can go for drawing the schematic, stick diagram, and subsequently the layout for the same thing. Now let's quickly convert this information to a graph network. So I am starting from here. Let's find out what are my nodes. Now let's take a PMOS network. Look at this. VDD is one of my node. This is another one node. This is another one node. Right? Now all the other things are transistors. So I'm just fixing it up like a graph for a PMOS. So top you have VDD. Let me keep the junction point this as somewhere here. Another junction point this as your Y. Okay. Now between this VDD and this point, say let me temporarily keep some point this as something like X. Okay. So between X and VDD you have a transistor A sitting to that. So this is my A. Similarly between X and, so this point is my X. Okay. Temporarily I am giving some node. Between X and Y you have one more transistor which is running in parallel, B, and another one which is running in parallel, C. That's it. So you have A, B, C. Similarly, let me take it for a PMOS network. This is for a PMOS. Let me take it for an NMOS. NMOS, you start from say Y. Then let me have this point to be Z point. So one node is Z, another one is ground. Right? These are the three vertex. So between Y and Z you have B. So this is to be my B. Between Z and ground you have C. So this is my C. Between ground and Y you have A. So I have connected my A. That's it. So this topology is for an NMOS. So we have completed two steps of this. That is, we have created a graph for the schematic. Second thing, I am supposed to see that which pattern which will go through all nodes and edges. Now let me try one thing. Let's start from here. This is my first node. Starting from here, going through A, B, and coming to C. So the order is A, B, C. This is one order. Let me see whether this same order fits here also. A, B, C. Yes. So I have one pattern which is A, B, C which is happening for my NMOS network. That is, it's like going here. A, B, C. So it is going through all nodes and all edges. The same thing I could follow here also. A, B, C. One more point. You can start at any node in your graph. So this may not have a unique solution. You may be having numerable solution, n number of solution for this particular problem. So this ABC can also be a solution for both PMOS and NMOS because this pattern is satisfying both NMOS network and PMOS network. Let me consider like this. Can I have a path something like this? starting from Y, C, or C, B, A. I can have something like this. C, B, A. C, B, A. Yes, that's also possible. So I can have C, B, A. C, B, A. Remember, it's a cyclic thing. You can keep on rotating that order. So here A, C, B. A, C, B. This could also be a solution, right? But there are some cases where a particular pattern will be suitable for an NMOS network. Sometimes the same order may not be suitable for a PMOS network. Under that case, you are not supposed to use those patterns, because the third rule says follow or use same pattern which is following or which is suitable for both NMOS network and PMOS network. So as of now, the solution is, it could be ABC, CBA, or you have still n number of solution, right? As I said, it has it doesn't have an unique solution. You can have n number of solution. Now let us consider only one solution, ABC, and let's try to come up with an optimized stick diagram for the same. Right. So I am trying to come up with an optimized stick diagram for this particular function y equal to a plus bc the whole bar using Euler's graph. So what we have decided is, for any stick diagram, you are supposed to have two metal layers. At the top you have VDD. This becomes mandatory. You can better draw for all the stick diagrams, whichever you have drawn. So two power lines I have drawn. Now the next thing is, for the whole NMOS network, I am using a single N diffusion. Remember, this N diffusion, I am not breaking that N diffusion. In the previous example, I have showed you that we have broken as many number of N diffusion, and thereby it creates too many capacitance and many problems. So this is my N diffusion. Similarly, for the PMOS network, on the whole, I am going to create one P diffusion. We use different colors. While drawing the stick diagram, we recommend you to use the corresponding color pencils or color sketch for drawing of this stick diagram. That is mandatory. So the top you have P diffusion and the bottom you have N diffusion. The next thing is drawing of polylines. Now here comes the Euler theorem. This Euler theorem says you can follow this order ABC or CBA or any other order also. Now I am following the first order ABC, which satisfies both the NMOS and PMOS. So draw three polylines which is common for both PMOS and NMOS network. So this is my A, B and C, three polylines. See, this order is important. This is what I said, or only this order makes my network to be optimized in the way of sharing the diffusion. Okay, fine. So you are using three polylines in the order of ABC. Now get back to this schematic which you have drawn. This is my source. Again, these are my drains, right? So these are my drains, source, drain. Now the source of N, the source of C and the source of D, right? Source of C, source of C and source of D sorry not D, source of A should be connected to ground. Source of C, source of D. Let me keep it like this. Since these two are different materials, this is metal and this is a diffusion, I am using a contact there. So this is clearly source of C is connected to ground, source of A is being connected to ground. Now, remember, drain and the source of PMOS are being shared among these two. Drain of C and the source of B has been shared. This node is the shared node. Since we don't take any output here, I am just leaving it. But remember, that is the shared diffusion. This point is acting as a drain for this as well as source for B. Again, drain of B is being connected with the drain of A, and the same thing has been taken for Y. So, if I take a contact from this point, this is typically same as connecting these 2 points and taking Y. Am I right? So, this I am taking and representing this as Y. Any doubt? So, quickly I will again refresh here. See, the source of A, source of C has been connected to ground. So, this is my C polyline. Either end you will have source and drain. Similarly, A, either end you will have source and drain. B, source and drain. One end I am connecting here. This one end of the C is being connected here. So this becomes the source here. One end of the A I am connecting here. This becomes the source here. This is the shared of connection of A and B. I am taking the output from that point. The shared point of B and C, we don't take any output, but it is a shared. The same thing I am discussing with respect to PMOS network. Here you can see one end of the one end of the A MOSFET source has been connected to VDD. So typically I am connecting this to VDD. So this is my source. The other end of the A terminal is being in common with B and C and that with A. B and C and that with A. And B and C is being connected with Y. Let's see, look at this. B, C, their common node is being connected with Y. Which is the common node for B and C? This is my common node for B and C. Correct? So I am simply taking that common node and connecting that to Y. So this point is connected. One more thing. What does it say? A, B, C should be connected. A, B is a common point that has to be connected with C. Now, look at here. These two nodes need to be connected with each other. So, these two are connected. Because this point is A, B and C node. A, B common point and the C node has been connected. So this will establish my stick diagram, optimized stick diagram for this function A plus BC the whole part. Now here, important thing what you can notice, the number of contacts is low. There is a shared diffusion. All this happens because of ordering this poly and placing that poly in common with your PMOS network and your NMOS network. This naturally gives me an optimized stick diagram for any Boolean function which we have taken. So I think you can extend this for any of the Boolean functions, and the same thing could be drawn as a stick diagram. Later on, the whole thing again can be converted to a layout. As a homework, I would like to give two such problems for coming up with an optimized layout. One, bring an optimized stick diagram for the function a plus b c d. This is one. And second one, bring an optimized stick diagram for this function. That's all. So as a quick recap, so what we have done is, we have seen what could be the graphical representation of a schematic. After doing that, we have applied Euler's theorem in order to find out what could be the order of the poly. Once we found the order of the poly, we make sure that the order of the poly satisfies both PMOS network and NMOS network. From there again I went on with drawing the stick diagram for the same. Stick diagram, as usual, like you have my power lines, you have a common diffusion without any break, like N diffusion and a P diffusion. And for that, you have drawn the order of the poly ABC. From there again, looking this picture schematic, we have completed the sketching of stick diagram. Now the stick diagram doesn't have any break in the diffusion, and it has minimum number of contacts, thereby minimum number of capacitance and low area, power and the timings. Now how to extend this for a layout? So as I said earlier, layout, the difference between a layout and a stick diagram lies only with the dimension. Means a stick diagram with appropriate dimensions is equal to layout. There is nothing else. So if I draw the same stick diagram with appropriate dimensions, by dimension what do I mean is their exact length, width, all those details, then it becomes the layout. So for the layout, there are three rules or three dimension rule. One is minimum length and width rule. Say for example, if I am drawing a polyline, if it is a stick diagram, I would show that as a single line. If it is a layout, it will be shown as a layer, and the minimum dimension will be something, it would be represented as 2 lambda. I will get back to this lambda shortly. But remember, every dimensions would be represented by the minimum length, width, everything will be represented by certain amount of lambda, 2 lambda, 3 lambda, 5 lambda, where lambda or 2 lambda equal to minimum channel length. So lambda is minimum channel length by 2. Say suppose if I am working with 600 nanometer technology, so my lambda is 300 nanometer. 300 nanometer. So if at all if I am using a polyline, the polyline width should be 600 nanometer. Anything less than this 600 nanometer will lead to the violation of minimum length and minimum width violation. Second thing is minimum spacing rule. spacing rule. This rule says something like this. If I am having two metal lines, say metal line 1, metal line 2, what should be the spacing between these two metal lines? What should be the spacing? Say suppose it is 3 lambda. What does it mean is, any two layers should be separated by a minimum amount of 3 lambda or 4 lambda, whatever the prescription says in the layout rules, that should be followed. This is called spacing rules. The third rule is overlap rules. Rule of overlap. Say, I am using N diffusion. Over this, I am using a poly. Now this says something like this. This rule says, what should be the minimum overlapping length and width? What should be the minimum extension after this overlap? So this type of rule is called as overlap rules. So whenever one layer cross another layer, what should be the minimum extension beyond that particular overlap? What should be the minimum layer of interface between those two layers? So this information, say suppose if this is N diffusion, this is poly, this should be 2 lambda, this should be 2 lambda. So totally it should be 2 lambda cross 2 lambda. So under these three categories, you have set of rules for different layers, right? And this has been given as set of layout rules for every technology file which has been given by the fab. Say suppose if I am using 180 nanometer technology, this rule should have been listed there. For drawing any layout, you can just refer those list of rules. Say it would be stated like this: minimum length of the polysilicon layer is, minimum width is 2 lambda, length is 5 lambda. Minimum width of a P-well is 10 lambda. Minimum width of a metal layer is 3 lambda. So like this you have a set of rules. These rules you can cross-refer with the layout rules which has been given, and at the end of drawing the layout, you can go for the option of DRC, Design Rule Check. Any violation in these layout rules will be highlighted by the tool, and that could be recorrected. And when once all the layout rules are being satisfied, then that leads to the formation of an effective optimized layout for that particular CMOS structure which you aim for. I hope this lecture which given you an insight of how to draw a stick diagram, how to draw a layout. Probably you can extend the same thing to draw a layout, except only thing, wherever I have drawn a line, that will be a layer with appropriate dimensions of length and the width. So wherever I placed a contact, there will be a contact. This contact is metal and a diffusion contact. Like this, at different places, you will have contacts, layers, and their appropriate dimensions would have been given. So you may cross-refer again what are their minimum rules that stated by every technology file, and you can draw the layout and cross-check for DRC. This will lead to an efficient back-end designer. Thanks for listening. We will meet how to find out the delay in the next couple of lectures for any CMOS network. When a CMOS network is given, how to find out the delay. Thank you.